What happens when something enters our solar system that does not behave like anything we've seen before? That is the question surrounding TR3 Atlas, the interstellar visitor that has puzzled astronomers since its discovery. From the very first moment it was spotted, it challenged assumptions. Was it a comet, an asteroid, or something altogether new? Objects like TR3 Atlas are not common. The solar system is busy, but most of the rocks, comets, and asteroids we see are bound by the sun's gravity. They follow predictable paths, orbiting again and again. Interstellar objects, on the other hand, are rare guests. They come from far beyond, traveling across the emptiness of space for perhaps millions of years before drifting into our cosmic neighborhood. That alone makes TR3 Atlas special. But what has kept scientists and the public so captivated is not simply that it arrived from elsewhere, it is the way it behaves. Early on, TR3 Atlas didn't fit neatly into any category. Its brightness fluctuated. Its chemical composition looked strange. And most mysterious of all, it didn't show the clear, extended cometary tail that observers expected, at least not at first. To understand why this matters, we need to recall the handful of other interstellar visitors we've seen before. The first, in 2017, was Oumuamua. It streaked through our solar system with a shape unlike anything astronomers had ever recorded. Long, thin, and tumbling. Its unusual path and lack of a visible tail led some to even wonder if it was artificial. Just 2 years later, Comet Borisov arrived. Unlike Oumuamua, it behaved like a normal comet, venting gas and dust in a familiar way, proving that interstellar objects could look much like the icy bodies we know. TR3 Atlas seems to fall somewhere between those examples. It is not as puzzling in shape as Oumuamua, but not as straightforward as Borisov either. Its signals suggest cometary activity, but the details don't quite align with expectations. This ambiguity is what makes it so important. Each interstellar visitor gives us a chance to understand what planetary systems beyond our own might look like. Each one is a messenger carrying chemical clues about the wider galaxy. And now, thanks to new observations, astronomers are beginning to peel back the layers of this mystery. On August 23, 2025, an image taken from Brazil offered fresh insight into the nature of TR3 Atlas. It may look faint, perhaps even unremarkable to the untrained eye, but to scientists, it carries meaning. It shows the first evidence that TR3 Atlas may indeed be sprouting a tail. Small, difficult to see, but real. This changes things, because a tail means activity. It means sublimation. Frozen gases on the object's surface turning into vapor as they warm under the sun's light. That process is the hallmark of a comet. And if TR3 Atlas is behaving like a comet, even faintly, then we may be witnessing the early stages of its transformation as it journeys deeper into the solar system. Yet, as we will see, the story is more complex than it sounds. Detecting this tail is not easy, and its orientation defies what casual observers might expect. The mystery is not solved. It is only deepening. On August 23, 2025, a small observatory in Brazil quietly captured an image that would ripple across the astronomical community. The Sonar Observatory, located in the Serra da Piedade Mountains of Minas Gerais, recorded TR3 Atlas under carefully controlled observation. At first glance, the picture might appear modest compared to the dazzling high-resolution views offered by space telescopes, but its importance lies in what it revealed. the faint beginning of a cometary tale. For scientists, this was a pivotal moment. The object that had long appeared ambiguous was finally offering a sign of comet-like behavior. Until then, debates had been fierce. Some argued that TR3 Atlas was behaving too much like a bare rock to be classified as a comet. Others insisted it had to be icy, merely waiting to warm enough for gases to escape. This single image did not settle the matter completely, but it tipped the balance toward the cometary interpretation. What makes the Sonier Observatory's contribution especially significant is its origin. Brazil is not often the first place people think of when discussing major astronomical breakthroughs. Yet here, in South America, a dedicated team provided data that the entire world is now scrutinizing. The observatory itself, whose name stands for Southern Observatory for Near-Earth Asteroid Research, has carved out a role in tracking asteroids and comets that come close to Earth. Its vantage point and persistent observations make it a valuable contributor to planetary defense and interstellar research alike. The August 23rd observation fits into a larger timeline of global effort. Observatories across the world, from giant facilities in Chile to backyard telescopes in Europe, have been attempting to follow TR3 Atlas since its discovery. But conditions, timing, and equipment matter. That day in Brazil, the sky was clear, the instrument calibration precise, and the result was a frame showing something new, a faint but measurable extension trailing the object. It is worth pausing here to consider why such an image is important. In astronomy, context is everything. A comet's activity is not only a matter of visual appearance, but also of physics. Sublimation releases dust and gas that scatter sunlight, forming a glowing tail. Seeing one emerge provides confirmation that the body is volatile rich, carrying frozen materials that date back to its origin. For TR3 Atlas, an object arriving from another star system, those frozen materials may contain signatures of chemistry shaped far from our Sun. The Sonier team did not work in isolation. Their data has already been compared with observations from elsewhere, including the James Webb Space Telescope. Together, the contrast between ground-based and space-based observations paints a fuller picture. Webb looks at composition, at the invisible fingerprints of molecules. Sonier looks at structure, at the broad features across the sky. Both perspectives are necessary. In essence, that single frame from August 23rd is more than a photograph. It is evidence. It is a clue in the ongoing investigation of what TR3 Atlas really is. And while it raises as many questions as it answers, it represents one of the first moments where speculation began to give way to measurable science. But before we can appreciate just how challenging this detection was and why it matters so much, we need to understand the difficulty of observing cometary tails in the first place. Because what looks simple on paper is in reality shaped by geometry, sunlight, and perspective. When we think of astronomy's great centers, we often picture the deserts of Chile with their massive telescopes, or NASA's facilities in the United States, or perhaps Europe's observatories perched on mountaintops. Rarely do we think first of Brazil. Yet, with the Sonier Observatory's capture of TR3 Atlas, Brazil demonstrated once again that astronomy is not limited to the biggest institutions, but thrives wherever there are committed scientists and clear skies. The Sonier Observatory, short for Southern Observatory for Near-Earth Asteroid Research, has been operating with a very focused mission, tracking near-Earth objects. These are asteroids and comets that come close enough to pose a potential risk to our planet. Monitoring them is a task of global importance, one that requires international cooperation. SONIR is the only observatory in Brazil fully dedicated to this kind of research. And while it may not have the immense power of a space telescope like Hubble or Webb, its ability to provide timely, wide-field observations has made it invaluable. The capture of TR3 Atlas on August 23rd highlighted just how significant such contributions can be. Brazil provided not only a geographical advantage, the southern hemisphere sky offers perspectives unavailable to northern observatories, but also a demonstration of how smaller facilities can fill crucial gaps. Sometimes the most important data is not the sharpest image or the deepest spectrum, but simply being able to point a telescope at the right place, at the right time, and document what happens. For the global scientific community, SONIR's involvement was more than symbolic. It reinforced the principle that astronomy is a collaborative science, not dominated exclusively by large powers. Every observatory, whether in Brazil, South Africa, or a backyard in Spain, adds a piece to the puzzle. In the case of interstellar objects like TR3 Atlas, where data is limited and observation windows are narrow, each contribution can shift the balance of understanding. Brazil's role here also speaks to the democratization of astronomy. With access to technology, training, and networks of international cooperation, smaller observatories can directly impact global science. This is not the first time Brazil has played a part. In past years, Brazilian astronomers have discovered asteroids, monitored comets, and contributed to the international tracking network that helps guard against potential collisions. TR3 Atlas, however, has placed them on a larger stage. And for the public in Brazil, this achievement carries another layer of meaning. It is a reminder that scientific discovery is not confined to distant institutions, but can happen in their own country through the work of their own scientists. The image of TR3 Atlas, released by SONIR, is not just data. It is a point of pride, a moment of participation in humanity's collective quest to understand the universe. But this image revealed more than just Brazil's role. It provided the first tangible evidence that TR3 Atlas is behaving like a comet. Faint though it was, the tail began to emerge. And that discovery brings us to the next critical question. Why is observing a comet's tail such a challenge, and what can it really tell us? When astronomers examined the image from SONIR Observatory, they noticed something subtle but unmistakable. A faint streak of light trailing from TR3 Atlas. To the untrained eye, it might appear as little more than a blur. But for those who understand how comets behave, this was the first whisper of activity, the earliest sign that the object was venting material into space. This is a key turning point. A comet is defined not by its shape or size, but by its activity. When frozen gases and dust locked inside its body begin to heat under the sun's radiation, they sublimate, transitioning directly from solid to gas. That outflow creates an atmosphere, called a coma, and from there, solar wind pushes the material outward, forming the comet's signature tail. If TR3 Atlas was beginning to show even a small amount of this behavior, then it was shifting categories. It was no longer simply a mysterious rock drifting through interstellar space. It was revealing itself as an active comet. But this tail was not grand or dramatic. It was not like the sweeping arcs captured in famous photographs of comets such as Hale-Bopp in 1997. or comet Neowise in 2020. Instead, TR3 Atlas's tail was timid, just beginning to emerge, visible only through careful observation and analysis. It is a reminder that nature rarely provides us with easy answers. Identifying activity in its infancy requires patience, precision, and context. The context, in this case, was crucial. Astronomers had long suspected that TR3 Atlas might start showing signs of activity once it crossed a certain threshold of solar heating. Predictions suggested that by early August, the object would either confirm its cometary nature or remain stubbornly inactive. For weeks, telescopes around the world kept watch. Many saw nothing unusual. Then came the August 23rd image from Brazil, a narrow window of time, a moment when conditions aligned just right to reveal what had been hidden. The excitement was immediate. If TR3 Atlas could display even a faint tail now, it meant more activity might follow. As it journeys deeper into the inner solar system, closer to the Sun, sublimation will likely increase. Each day could reveal more gas, more dust, and a clearer picture of its true nature. Yet the faintness of the tail also raised questions. Was TR3 Atlas unusually volatile poor, carrying only a thin supply of frozen gases compared to most comets? Or was the geometry of its position simply making the tail difficult to see from Earth? These questions did not diminish the importance of the finding, but they reminded scientists that one observation is never enough. To solve the puzzle of TR3 Atlas, a series of careful, coordinated studies would be required. This first glimpse of activity was the spark. But the real challenge was only beginning. Understanding why this tail was so elusive and why its orientation defied the expectations of casual observers. At first, it might seem simple. If comets form tails when they approach the Sun, then surely those tails should be easy to spot. Bright streams of light trailing behind like banners in the sky. But reality is more complicated. Observing a comet's tail depends on geometry, brightness, and perspective. For TR3 Atlas, each of those factors made detection more challenging than expected. A comet's tail is not random. By definition, it always points away from the Sun. This is because the solar wind, a continuous flow of charged particles streaming outward, pushes dust and gas directly opposite to the Sun's position. In most cases, this geometry is straightforward. The Sun sets in the west, rises in the east, and a comet's tail extends predictably in the opposite direction. But TR3 Atlas is not behaving under ordinary circumstances. During the time of observation, the Sun's position in the sky was unusual. Coming after the solstice, the Sun was displaced toward the south, shifting the geometry of sunrise and sunset. This meant that from Earth's point of view, the comet's tail wasn't lining up neatly with the east-west path observers instinctively expect. Instead, it appeared inclined, tilted at an angle that made it harder to detect. To the eye of a casual stargazer, it might even have seemed absent. Only through careful alignment of instruments, long exposures, and comparisons with background stars could astronomers confirm that a faint tail was indeed emerging. What looked like a subtle blur of light was in fact the beginning of cometary activity. This difficulty is not unique to TR3 Atlas. Astronomers often encounter situations where geometry hides what physics is producing. A comet may be releasing dust and gas, but if the tail is pointing nearly toward us, or angled in a way that blends into the brightness of the sky, it can remain practically invisible. The absence of a visible tail, therefore, does not mean the absence of activity. It may simply mean that Earth's vantage point is poorly aligned to see it. For TR3 Atlas, this made the August 23rd detection particularly significant. Despite the odds, despite the tail's awkward orientation, astronomers captured its emergence. That faint trace told them not only that the object was active, but also that geometry was playing tricks on perception. What seemed at first to be an inert interstellar rock was, in fact, slowly awakening under the sun's influence. Yet geometry alone did not fully explain the strangeness of the observation. The tail was not only faint, it was inclined at a strikingly unusual angle of about 102 degrees, adding a further layer of complexity. To understand why, scientists turned to analogies, bridging technical detail with intuitive explanation. When astronomers measured the tail of TR3 Atlas, they noted something peculiar. It was tilted at an angle of about 102 degrees. For a comet's tail, this is unusual. Instead of extending in the neat, predictable direction opposite the sun, the tail appeared displaced, almost misaligned with the geometry most observers would expect. Why does this matter? Because the orientation of a comet's tail is one of its most defining characteristics. For centuries, comets have been described as stars with tails, their luminous streams drawn across the heavens in sweeping arcs. Those tails, always pointing away from the sun, are usually easy to predict. But in the case of TR3 Atlas, its inclination made the tail appear to defy expectations, leaving many amateur observers puzzled. The explanation lies in the subtle dance between the sun's seasonal position and our vantage point from Earth. At the time of observation, the sun was shifted southward, following its path after the solstice. Sunrise and sunset were no longer aligned strictly east-west, but slightly offset. This altered the celestial reference frame so that a tail pointing directly away from the sun did not align with the intuitive line most people expected. To astronomers, this was not a mystery, but a matter of geometry. Still, the result was counterintuitive. A tail that looked out of place, leaning at a sharp angle. Detecting it required careful understanding of how the sun's position distorts our frame of reference, and how Earth's position influences the apparent orientation of objects in the sky. The 102-degree tilt was not random, nor was it evidence of something unnatural. It was, instead, a reminder of how easy it is for perception to mislead. Without understanding solar geometry, it might seem as if TR3 Atlas were violating the rules of physics. In truth, it was behaving exactly as expected, only under conditions that made the outcome appear strange. This subtle but critical point highlights the challenge of communicating astronomy to the public. What seems obvious, a comet has a tail, so just look for it, can in reality depend on a web of invisible factors. TR3, Atlas's unusual tail inclination, became both a scientific puzzle and a teaching moment, a way to show how science peels back the layers of illusion to reveal consistent natural laws at work. Yet explaining this to the general audience required more than numbers and degrees. Astronomers turned to analogies, drawing comparisons with everyday experiences to show why the tail was so hard to see and why its position appeared unusual. To make sense of TR3 Atlas's tail orientation, astronomers reached for an analogy, something simple enough for anyone to understand. Imagine standing by a railway track. A train approaches from the distance, heading straight toward you. From your perspective, you see the locomotive at the front. But the carriages behind it? They line up so perfectly with the engine that they vanish into its shape. Unless the train turns slightly to one side, you cannot distinguish the rest of it. This is similar to how TR3 Atlas's tail behaves when observed from Earth. If the tail points in a direction nearly aligned with our line of sight, much of its structure becomes difficult to separate from the object itself. It is there, extending outward, but perspective hides it, just as the train's carriages hide behind its front engine. The analogy helps explain why casual observers might think the comet has no tail. In reality, the tail is present, but the angle of view compresses it, blending faint material into the background sky. Only with sensitive instruments and careful exposure times can astronomers tease out the signal, detecting what human eyes would easily miss. This challenge highlights an important truth in astronomy. What we see is often shaped more by perspective than by the object itself. The cosmos obeys physical laws, but our vantage point can distort appearances. TR3 Atlas's 102-degree tail inclination did not mean it was breaking rules. It meant Earth's geometry, the sun's seasonal shift, and the comet's trajectory combined to produce an odd, misleading alignment. By using comparisons like the train, astronomers bridge the gap between complex orbital mechanics and human intuition. It is not that TR3 Atlas refuses to grow a tail. It is that from where we stand, the view hides most of it. Yet even with this explanation, the discovery carried weight. The tail was beginning to emerge, faint but real, and that timing matched a key prediction. Astronomers had long expected that TR3 Atlas would start showing signs of activity around early August. The sonar image confirmed those forecasts, right on schedule. From the earliest observations of TR3 Atlas, astronomers knew the clock was ticking. Interstellar objects that pass through our solar system do not linger. Their trajectories are hyperbolic. One pass near the sun, and then they are gone forever, flung back into interstellar space. That urgency meant scientists had only a short window to study TR3 Atlas before it disappeared beyond reach. Predictions suggested that if TR3 Atlas was indeed a comet, it would begin showing signs of activity around early August 2025. The reasoning was simple. As it drew closer to the sun, solar radiation would heat its surface, sublimating frozen gases and creating a faint coma and tail. If nothing appeared, then perhaps TR3 Atlas was more asteroid-like, a bare rock without significant volatile content. For weeks, telescopes around the globe tracked the object, waiting for any change. Some nights yielded nothing unusual. TR3 Atlas remained just a faint speck, no more alive than an ordinary asteroid. This created tension. Was it possible that scientists were wrong? That the object was fundamentally different from comets we know? Or was the activity simply too subtle to see? Then came the Sonar Observatory's August 23rd image. Almost exactly in line with forecasts, the faint beginnings of a tail were visible. It was not large, and it was not obvious, but it was there. The prediction had been correct. TR3 Atlas was awakening. This confirmation carried weight far beyond a single observation. It validated the models predicting its activity threshold. It demonstrated that scientists could anticipate when frozen gases on an interstellar object would begin to vent, even though this was only the third such object humanity had ever observed. And it reinforced the idea that TR3 Atlas, while strange in some respects, was fundamentally cometary in nature. Yet, the faintness of the tail also reminded researchers of how complex these objects can be. Activity begins gradually, with tiny amounts of sublimation. Only as the object continues inward toward the Sun does the process intensify, producing the spectacular tails seen in bright comets. TR3 Atlas was still early in that journey. The timing also helped settle debates. Had activity not appeared by late August, many would have leaned toward the asteroid hypothesis. Instead, the August 23rd image shifted the balance. TR3 Atlas might not be a comet in the traditional sense, but it was certainly behaving more like one than any other category. And this wasn't the only comet making astronomers puzzle over faint or absent tails. Around the same time, another object, comet C2225A6, Lemon, was also refusing to show a clear tail, even though it was closer to the Sun. Comparing the two offered fresh insight into how cometary activity is sometimes far less obvious than popular images suggest. The faintness of TR3 Atlas's tail led many to ask, is this unusual, or is it something comets often do? To answer that, astronomers turned to comparisons. One of the clearest came from another comet observed around the same period, comet C2025A6, better known as Lemon. Comet Lemon was closer to the Sun than TR3 Atlas, which in theory should have made its activity more pronounced. When comets move inward, sunlight heats their icy surfaces, causing them to vent large amounts of gas and dust. The closer the distance, the stronger the activity, and the brighter the tail should be. Yet, in the case of Comet Lemon, telescopes showed almost no visible tail. Even under favorable conditions, its activity remained subtle, nearly invisible. This parallel mattered. It demonstrated that TR3 Atlas was not alone in its behavior. Cometary activity is not always dramatic. Some comets erupt in spectacular displays, while others remain faint, their tails barely distinguishable from the background sky. The difference can come down to composition. How much volatile ice the comet carries, how porous its surface is, and whether layers of dust cover its nucleus, shielding frozen material beneath. For the public, who often picture comets as grand streaks across the night sky, this can feel disappointing. But for scientists, it is a crucial reminder. The absence of a visible tail does not mean the absence of cometary processes. Just as with Lemon, TR3 Atlas might be actively venting, but in a way that is difficult to detect from Earth. These subtle cases help refine our understanding of cometary physics. They show how geometry, surface chemistry, and solar position all conspire to shape what we see, or fail to see. And in the case of TR3 Atlas, the faint tail observed by sonar suggested that activity was beginning, even if modestly. It was one more piece of evidence pushing the interpretation toward comet rather than asteroid. Yet the comparison also pointed toward a larger issue. The tools astronomers use matter enormously. A faint tail may be invisible in one telescope and detectable in another. Which is why, in addition to ground-based observatories like SONAR, astronomers also turn to the most powerful space telescope ever built, the James Webb. When studying an object as unusual as TR3 Atlas, the choice of instrument can change the story entirely. Ground-based telescopes like Brazil's SONAR Observatory provide one perspective. They capture wide fields of view, offering context in the sky, and making it possible to detect extended structures like cometary tails. But space-based instruments, such as the James Webb Space Telescope, JWST, serve a very different role. They look deeper. peeling apart light to reveal the object's composition at a molecular level. The difference is often misunderstood. To the public, one telescope might appear better than another. Webb is vastly more powerful in sensitivity, capable of detecting faint galaxies billions of light years away. By comparison, a smaller observatory like SONIR seems limited. Yet in this case, the smaller, wide-field view was precisely what was needed to reveal the faint extension of TR3 Atlas's tail. Think of it as two complementary tools. Webb is like a microscope. It zooms in with unmatched precision, breaking light into spectra to identify elements and molecules. But microscopes see only small fields of detail. SONIR, on the other hand, is like a wide-angle camera. Less detail, but more context. Both are essential to form a complete picture. Without SONIR, the faint tail might have gone unnoticed. Without Webb, the chemical fingerprint of TR3 Atlas would remain unknown. This comparison also highlights the challenges astronomers face in communicating science. When Webb released its first dataset on TR3 Atlas, many expected a dazzling photograph. Instead, what they saw was raw data, spectral lines and pixelated detections. Some dismissed it as unimpressive, even questioning why Webb's images didn't look as clear as ground-based photographs. The reality is that Webb was not taking pictures. It was collecting the kind of light information needed to decode the object's chemistry. The key lesson is that no telescope alone can answer every question. Each is designed with strengths and limitations, and when they work together, they create a synergy. For TR3 Atlas, SONIR revealed structure, Webb revealed chemistry, and together they moved the mystery one step closer to clarity. Yet what Webb found in those spectra was even stranger than the orientation of the tail. An unexpected chemical signature, one that made TR3 Atlas stand out from nearly every comet astronomers had studied before. When astronomers debate which telescope is better, they often overlook that different instruments are designed for different purposes. TR3 Atlas is a perfect example of why both wide-field ground observatories and ultra-sensitive space telescopes are needed to unlock cosmic mysteries. The SONIR Observatory provided the kind of wide-angle vision that is essential for catching the full extent of a comet's tail. Its instruments may not resolve fine details, but they can capture more of the sky at once. For detecting something as faint and extended as a newborn cometary tail, that broad coverage is invaluable. Without it, TR3 Atlas's activity might have gone unnoticed until much later. On the other hand, the James Webb Space Telescope excels in sensitivity. It gathers more light than almost any other telescope ever built, focusing on tiny details invisible from Earth. But Webb's strength is not in broad snapshots. It is in precision. With Webb, astronomers can split light into spectra, detecting the chemical fingerprints of molecules like carbon dioxide, methane, or water vapor. That is not something a telescope like SONIR can do. In a sense, SONIR and Webb are two halves of the same story. SONIR shows the comet's behavior, its tail, its geometry, the way it interacts with sunlight in real time. Webb shows its composition, the chemistry that defines what it is made of, and, perhaps, where it came from. Alone, each gives an incomplete picture. Together, they reveal TR3 Atlas as both a physical traveler across the sky and a chemical messenger from another star system. This division of labor is not unique to TR3 Atlas. It applies to astronomy at large. Ground-based and space-based instruments complement each other. One observes scale, the other detail. One sees context, the other substance. Only by combining both can astronomers approach the truth. For TR3 Atlas, that truth became stranger than expected. Webb's data revealed something extraordinary, an unusual abundance of carbon dioxide, unlike what scientists typically see in comets closer to home. This finding would reshape the debate around the object's identity, hinting at origins far different from those of the frozen bodies in our solar system. When the James Webb Space Telescope turned its gaze toward TR3 Atlas, many expected breathtaking images, colorful, sharp, and full of detail, like the ones Webb has delivered of distant galaxies and nebulae. But what astronomers received instead looked, to the public, disappointing. Noisy charts, pixelated images, and what some critics dismissed as ugly data. That reaction misses the point. Webb is not designed to take pretty pictures of nearby comets. Its power lies in spectroscopy, the ability to break light into its component wavelengths and detect the fingerprints of specific molecules. Those jagged lines and blurred spots are not mistakes. They are coded messages, revealing the chemistry of an object billions of kilometers away. In the case of TR3 Atlas, Webb's spectroscopic data told a remarkable story. It showed unusually high levels of carbon dioxide gas being released from the object. This was not a photograph of a glowing tail, but a direct measurement of its molecular composition. Such information is far more valuable to scientists than a postcard-like image. It tells them what the comet is made of, what ices are sublimating, and whether its chemistry matches anything we know from the solar system. Still, the contrast between Webb's data and Sonier's image highlighted the gap between public expectation and scientific reality. Sonier's picture showed a faint tail, the kind of visual evidence people instinctively understand. Webb's data, on the other hand, required expertise to interpret. For many outside the field, the significance was easy to miss. But for scientists, it was explosive. Because Webb had found something strange, TR3 Atlas did not look chemically normal. Compared to typical comets in our solar system, it carried a different balance of gases, particularly an excess of carbon dioxide. That composition hinted at an origin in an environment very different from the one where our own comets formed. This is why Webb's work is so critical. The telescope allows us to compare interstellar visitors not just in appearance, but in chemistry. Where they come from, how they formed, and what kinds of planetary systems exist beyond our own. All of these questions are hidden in their molecular signatures. And in TR3 Atlas, the signature was unlike anything expected. For the first time, astronomers were looking at an interstellar body that seemed to carry the chemical fingerprint of another world entirely. What Webb uncovered in TR3 Atlas was not subtle. The spectra revealed an unusually high concentration of carbon dioxide, far beyond what is typically measured in comets within our solar system. For scientists, this was a red flag, an indication that this object did not conform to the standard patterns they were used to. Comets closer to home usually carry a mixture of frozen water, carbon monoxide, methane, and smaller amounts of carbon dioxide. That balance reflects the conditions in which they formed: cold, but not extreme, and shaped by the chemistry of the early solar system. TR3 Atlas, however, tilted that balance heavily towards CO2. Its emissions suggested a nucleus rich in this gas, more than what Earth-based comets usually release. Why does this matter? Because the chemical makeup of a comet is a direct clue to its birthplace. Each planetary system forms with its own distribution of elements and compounds, depending on the conditions around its young star. Too much heat, and ices evaporate before they can become part of a comet. Too little, and different compounds freeze out at different distances, creating distinct chemical zones. In our solar system, that zoning left comets with relatively consistent compositions. TR3 Atlas appears to be different. The high CO2 levels raise the possibility that it formed in an environment colder or chemically distinct from anything in our solar system's history. Some astronomers even speculated it could resemble conditions near Mars, where carbon dioxide dominates the thin atmosphere and ice caps. To them, TR3 Atlas looked like a piece of a world sculpted in an alien system, something forged in a cradle of chemistry not seen here. This anomaly also helped explain the object's reddish tint. Carbon dioxide, when mixed with dust and other compounds, can create colors that differ from the dull grays of most asteroids or the icy brightness of some comets. The reddish surface of TR3 Atlas could be another sign of its unusual chemical fingerprint. For the scientific community, the discovery was thrilling and unsettling. Thrilling, because it offered a direct glimpse into the building blocks of another planetary system. Unsettling, because it challenged assumptions that interstellar objects would behave like the comets we already know. TR3 Atlas was not simply a wandering rock with a faint tail. It was now a chemical outlier, a messenger carrying evidence that the galaxy's diversity extends even into the icy fragments that drift between stars. The question that followed was obvious. If it carries so much carbon dioxide, could TR3 Atlas actually be a fragment of a planet, or even a planetesimal that once resembled Mars? As soon as Webb's findings were released, speculation began to circulate. The excess of carbon dioxide in TR3 Atlas was so unusual that some scientists wondered whether they were truly looking at a comet, or perhaps at something far stranger. Could this object actually be a fragment of a planet, broken off long ago and ejected into interstellar space? The idea is not as far-fetched as it sounds. In the early days of planetary systems, collisions were common. Planets and protoplanets crashed into each other with tremendous force, shattering surfaces and sending debris into space. In our own solar system, the Moon is thought to have formed after a giant impact between the young Earth and a Mars-sized body called Theia. If fragments can be blasted into orbit around a planet, they could also be ejected entirely, cast adrift between the stars. If TR3 Atlas is such a fragment, its chemical signature begins to make more sense. A piece of crust or mantle from a planet rich in carbon dioxide, similar to Mars, would naturally release CO2 as it warmed near the Sun. Its reddish hue could also be explained as planetary surface material weathered by cosmic radiation over millions of years. Of course, this is only a hypothesis. Confirming it would require far more data than current telescopes can provide. But the possibility is tantalizing. If true, TR3 Atlas would not just be a cometary visitor, it would be a shard of an alien world, a tangible piece of a planet that once orbited a star far from our own. That makes it one of the most scientifically valuable objects ever observed. Yet the planetary fragment theory also comes with complications. For one, TR3 Atlas's size and behavior still align with many features of comets. Its faint tail, its gradual sublimation, and its dusty coma fit the cometary model better than they do a planetary rock. To reconcile the two, some astronomers propose that it could be a hybrid, a fragment of a planetary body that retains volatile ices beneath its surface, now releasing gas like a comet as it warms. Whether comet, fragment, or something in between, TR3 Atlas is forcing scientists to reconsider definitions. For decades, comets and asteroids were treated as distinct categories, but interstellar visitors like this blur those lines, reminding us that the universe does not conform neatly to human classifications. The debate, however, also points to another challenge: understanding how science works in real time. To the public, these shifting interpretations can look like uncertainty or even contradiction. In truth, it is the process of science unfolding: raw data, evolving models, and the slow sharpening of understanding. For those outside the field, the way TR3 Atlas is being studied might seem confusing, even contradictory. One day, it looks like a comet. The next, it is compared to a planetary fragment. And then another data set suggests something else entirely. To the public, this can feel like uncertainty. But to scientists, it is the normal rhythm of discovery. Science does not reveal its answers in perfect clarity from the beginning. Instead, it advances step by step through raw, often messy data. Each observation adds a layer. Each measurement refines the picture. At first, the outlines are blurry, just as Sonier's faint image of a tail was barely distinguishable. Then with tools like Webb's spectroscopy, the structure sharpens. The process is cumulative, not instantaneous. This is especially true for interstellar objects. Unlike planets or nearby asteroids, they give us only one chance. TR3 Atlas is racing through the solar system on a hyperbolic trajectory. Once it swings past the sun, it will be gone, never to return. That urgency forces astronomers to work with partial information, building models as fast as new data arrives. It also highlights a cultural gap. Most people are accustomed to seeing finished results: glossy telescope images, polished explanations in textbooks. But the reality of research is different. Webb's ugly data charts are science in its rawest form, unrefined, yet already holding the secrets of chemistry from another star system. Sonier's faint images are not artistic photographs, but evidence, waiting to be measured and confirmed. For TR3 Atlas, this unfolding process is especially dramatic. Its behavior has moved from ambiguous to cometary, its chemistry from familiar to exotic, and its possible identity from comet to planetary fragment. Each step reshapes the debate, not because science is uncertain, but because each new observation adds complexity. In truth, this is how science progresses: through constant testing, questioning, and refinement. It is not weakness to change interpretations, it is strength. TR3 Atlas reminds us that we are watching discovery happen in real time, with all the unpredictability that entails. And what all the evidence now points toward is becoming harder to ignore. Whatever its origin, TR3 Atlas behaves more like a comet than any other category. Its faint but growing activity is the strongest sign yet that we are dealing not with a lifeless rock, but with an icy traveler from another star. By late August 2025, the pattern was becoming clearer. TR3 Atlas was no longer simply a mysterious object sparking speculation. It was showing consistent signs of cometary behavior. The faint tail observed by Sonier, the subtle emission of gases confirmed by Webb, and the timing of its activity all pointed in one direction. TR3 Atlas was a comet, albeit an unusual one. This conclusion did not come lightly. Early on, TR3 Atlas's behavior seemed ambiguous. Its brightness fluctuated, sometimes dimming in ways that did not fit standard comet models. For a time, the absence of a visible tail led some to argue that it was more asteroid than comet. A few voices even suggested artificial explanations, echoing the debates that surrounded Oumuamua in 2017. But as the evidence accumulated, those more speculative theories began to lose weight. What we were left with was a picture of an active body, venting gas and dust in response to the sun's heat. That is the hallmark of a comet. Even if its composition is unusual, rich in carbon dioxide, different from the icy bodies we know, its fundamental behavior aligns with what comets do. This makes TR3 Atlas not less interesting, but more so. Each comet in our solar system carries a record of early conditions billions of years ago. TR3 Atlas carries something even rarer, the record of another planetary system entirely. Its ices, its dust, its chemistry are all shaped by processes that occurred around a different star. By studying it, we are sampling the galaxy directly. The faintness of its tail, once seen as a weakness in the comet hypothesis, has become part of the story. Some comets are naturally subdued. Others only reveal their activity in certain geometric alignments. TR3 Atlas may be one of those cases, offering astronomers a chance to learn about the diversity of cometary behavior across star systems. Piece by piece, the case is being built. TR3 Atlas may not fit neatly into the molds we have created: asteroid, comet, or fragment, but it is acting more like a comet than any other category. And in science, behavior often counts more than labels. Yet as important as data and categories are, there is also the human side of this investigation. The astronomers who dedicate their time and effort to capturing these fleeting moments, sometimes from observatories far from the global spotlight. Their role in uncovering the truth about TR3 Atlas cannot be overstated. Behind every new image and dataset of TR3 Atlas are the people who made them possible. In Brazil, the August 23rd observations were credited to a team led by Cristóvão Jacques, co-founder of the Sonir Observatory. Jacques is widely recognized as one of the country's leading figures in asteroid and comet studies. And his decision to release the image publicly gave astronomers worldwide the chance to analyze the faint tail that marked TR3 Atlas's transition toward cometary behavior. Jacques has spent years working on near-Earth object monitoring, and his expertise provided confidence that what was seen in the image was not an error or artifact, but genuine activity. His contribution underscored the importance of local observatories in global science, institutions that may not have vast budgets or world-class equipment, but compensate with persistence, skill, and strategic observation. He was not alone. The analysis also benefited from input by Ari Martins, director of the Club de Astronomia Pleiades do Sul. Martins collaborated closely with the Sonir team, providing cross-checks and additional context to strengthen the interpretation of the data. In astronomy, collaboration is more than a courtesy. It is essential. No single observatory can provide the full picture, but when experts compare notes, weigh uncertainties, and combine perspectives, the result is more reliable. The acknowledgement of these names in official reports may seem like a small detail, but it illustrates how science is truly collective. Discoveries are not made in isolation by faceless institutions. They come from the work of individuals who dedicate long nights to observation, calculation, and verification. For TR3 Atlas, that human effort is what allowed the story to advance from speculation to evidence. It also reminds us that interstellar objects are a global responsibility. Whether in Brazil, the United States, Europe, or elsewhere, astronomers contribute whatever resources they have to study visitors like TR3 Atlas, knowing they will not get a second chance. Once such an object passes beyond the reach of our telescopes, the opportunity is gone forever. In the case of TR3 Atlas, those efforts have paid off. We now have images that show a tail, data that confirm unusual chemistry, and interpretations that narrow its identity toward comet. But the contributions of Jacques, Martins, and their colleagues are also part of the legacy. Their observations ensured that the world would not miss this fleeting messenger from another star system. And beyond Brazil, the study of TR3 Atlas also speaks to a larger truth. Astronomy thrives when nations and observatories cooperate, each adding their piece to a puzzle too vast for any one group to solve. TR3 Atlas may have been recorded in Brazil on August 23rd, but its story is being written by astronomers across the world. From amateur observers with modest backyard telescopes to the most advanced facilities orbiting Earth, the investigation of this interstellar traveler is a shared enterprise. Each observation adds context, each dataset fills in gaps, and together they form a mosaic of understanding. This global collaboration is not accidental. It is necessary. No single observatory, however advanced, can track an object like TR3 Atlas continuously. Clouds, daylight, and geographic limitations all restrict what one site can see. But with observatories spread across different continents, the object can be followed nearly around the clock. In effect, Earth itself becomes one great observatory, with astronomers passing data from time zone to time zone. History shows that this kind of cooperation has always been essential when studying interstellar visitors. With Oumuamua in 2017, it was rapid, worldwide communication that allowed astronomers to track its unusual trajectory before it left the solar system. With Comet Borisov in 2019, dozens of observatories contributed data that revealed it to be an ordinary comet from an extraordinary origin. TR3 Atlas is no different. Its fleeting appearance demands global coordination. Even small contributions matter. A faint image captured by an amateur astronomer may confirm brightness fluctuations. A spectrum from a medium-sized observatory might add one more data point to Webb's chemical analysis. The international network ensures no single moment is lost. And because TR3 Atlas is a once-in-a-lifetime visitor, every observation is precious. This spirit of collaboration also underscores a larger theme. Astronomy is one of the most global sciences we practice. Unlike many fields where competition dominates, studying the cosmos often brings nations together. No one country owns the stars. TR3 Atlas does not belong to any single observatory. It is passing through all of our skies, available to all who look up. For Brazil, the August 23rd image was a milestone, but for the world, it was one more piece in a shared effort to unravel what this object is. Whether comet, fragment, or something entirely new, TR3 Atlas is a puzzle that belongs to humanity. And in studying it together, astronomers demonstrate what is possible when knowledge is pursued across borders. As the data pool grows, scientists are beginning to piece together not just what TR3 Atlas is today, but how its activity has unfolded over time. By revisiting the timeline of observations, we can see how its cometary behavior has steadily taken shape. The evolving story of TR3 Atlas can only be understood by looking closely at its timeline. Each observation, each data set added a piece to the puzzle, and together They reveal how the object slowly shifted from an enigmatic speck to a confirmed comet-like body. The James Webb Space Telescope provided some of the earliest detailed data. On August 6, 2025, Webb captured spectra of TR3 Atlas while it was still relatively quiet. At that point, there was little to no visible cometary activity. Instead, the telescope focused on composition, detecting the unusual carbon dioxide signature that would later become the object's most defining feature. Though Webb's data did not show a dramatic tail, it supplied the chemical foundation that proved TR3 Atlas was unlike any local comet. 2 weeks later, the Sonier Observatory added the next piece. On August 23rd, its image revealed something new: the first faint trace of a tail. This was exactly what astronomers had predicted should happen if the object behaved like a comet. It was the moment when speculation gave way to confirmation. TR3 Atlas was awakening. The contrast between the two observations highlights the importance of timing. When Webb observed the object on August 6th, it was too early for significant sublimation. The sun's heating had not yet triggered enough outgassing to produce a visible coma. By August 23rd, conditions had changed. The geometry was still unfavorable, making the tail difficult to see, but it was there. This progression gave scientists confidence that their models were correct. Activity began almost exactly on schedule, just as calculations predicted. And as TR3 Atlas moved closer to the Sun, further increases in activity were expected. What was once an ambiguous interstellar visitor was now firmly trending toward cometary behavior. The timeline also reminded scientists of the urgency of their work. Each observation was a snapshot of a process that would never repeat. Once TR3 Atlas moves beyond the reach of our telescopes, the chance to study it vanishes. That is why the August 6th and August 23rd observations, separated by just over 2 weeks, are so crucial. Together, they mark the moment TR3 Atlas transformed from theory into evidence. And as astronomers compared these dates, they noticed something else. The object was not just glowing because of sunlight reflected off dust. It seemed to emit a strange light of its own, caused by physical processes happening on its surface. That raised the next question: what exactly was producing that glow? As TR3 Atlas drew closer to the Sun, astronomers noticed something curious. Beyond the faint beginnings of its tail, the object appeared to glow in a way that was not fully explained by reflected sunlight alone. To some, it almost looked as though the object were shining with its own energy. But the explanation was not mysterious. It was chemistry. When a comet-like body approaches the Sun, its surface heats unevenly. TR3 Atlas rotates, exposing different regions to solar radiation. The sunlit side warms up, and volatile ices, carbon dioxide in particular, begin to sublimate. That process releases gas into space. As the gas escapes, it drags dust with it, creating the faint coma and tail. At the same time, the escaping material scatters sunlight in distinctive ways, producing what looks like a subtle internal glow. This glow is not energy generated by the object itself. TR3 Atlas does not shine like a star, nor does it produce its own light. Instead, the brightness comes from sublimated gases reflecting and refracting sunlight, much like mist catching the glow of a street lamp. To an observer on Earth, it creates the impression that the comet is alive, radiating light, even though it is only interacting with the sun's energy. The effect is amplified by the rotation of the nucleus. As the comet spins, fresh surface areas are exposed to sunlight, releasing more volatile material. This intermittent sublimation can cause fluctuations in brightness, making the object appear to flicker. To astronomers, these changes are not random. They are clues about the comet's structure, its rotation period, and the distribution of ices across its surface. For TR3 Atlas, the phenomenon was particularly intriguing because of its unusual carbon dioxide composition. CO2 sublimates more easily than water ice at greater distances from the Sun, meaning TR3 Atlas could become active earlier than most comets. That may explain why even at the time of Webb's early observations, before the tail became obvious, the object already showed evidence of gas release. The glow, then, is not a mystery, but a confirmation. TR3 Atlas is venting material, responding to solar heating just as a comet should. It may not shine brightly, but its faint emission is proof that it is undergoing real, measurable change. Yet for all the scientific clarity, public fascination with TR3 Atlas also carried another dimension. Some wondered aloud, could an object this unusual, with such strange chemistry and behavior, be something more than natural? Could it, as with Oumuamua years before, be evidence of alien technology? Scientists address those questions directly. Whenever an unusual object crosses into the solar system, speculation about extraterrestrial technology is quick to follow. It happened with Oumuamua in 2017, and it happened again with TR3 Atlas. Its reddish hue, its faint and oddly angled tail, and its abnormal chemistry all fueled whispers. Could this be an alien probe disguised as a comet? Scientists took the idea seriously enough to test it, but the evidence points firmly toward a natural explanation. Every strange property of TR3 Atlas can be accounted for with physics and chemistry. Its odd tail? Explained by solar geometry and viewing angles. Its flickering brightness? A result of rotation and uneven sublimation across its surface. Its high carbon dioxide content? A clue to its origin in a planetary system different from our own. For astronomers, the test of an artificial hypothesis is simple. Is there any behavior that cannot be explained by natural processes? In the case of TR3 Atlas, the answer is no. Nothing observed, so far, requires an intelligent origin. Its trajectory follows the path of an interstellar body pulled by the Sun's gravity. Its activity is consistent with sublimation, and its chemistry, while unusual, fits within the range of natural diversity expected across the galaxy. The appeal of the spaceship theory lies less in evidence and more in imagination. The thought that we might not be alone is powerful, and interstellar visitors naturally invite such speculation. But science thrives on restraint. Without proof, clear, measurable proof, extraordinary claims must give way to the explanations grounded in physics. That does not make TR3 Atlas any less extraordinary. In fact, its value lies precisely in being natural. If it were artificial, it would be an anomaly, a one-off. But as a comet-like body with unusual chemistry, TR3 Atlas offers something more profound. Direct evidence that planetary systems around other stars produce objects unlike those we have cataloged here. It shows us that the galaxy is not uniform. It is diverse, surprising, and still largely unknown. The spacecraft theory may capture headlines, but the real wonder of TR3 Atlas is that it expands our picture of what comets can be. It demonstrates that even without alien technology, Interstellar visitors are messengers carrying secrets from distant stars. And those secrets are beginning to suggest that TR3 Atlas may have formed under conditions unlike any comet we have ever studied. If TR3 Atlas is not a spaceship, and if its cometary activity is undeniable, then the next question becomes, where did it come from? Its unusual chemistry suggests it did not form in the same conditions as the icy bodies of our own solar system. In our neighborhood, comets typically form in the Kuiper Belt or the Oort cloud, regions far from the sun where ices can survive undisturbed for billions of years. Their compositions are relatively consistent, dominated by water ice, with varying amounts of carbon monoxide, methane, and carbon dioxide. TR3 Atlas, however, breaks this pattern with its strong CO2 signature. This anomaly hints at origins in a system structured differently from ours. Perhaps TR3 Atlas was born closer to its parent star, where carbon dioxide could freeze more readily. Or perhaps it formed farther out, in a region where conditions allowed CO2-rich ices to accumulate in greater proportions. Either way, its chemistry suggests a story shaped by another star's history. Astronomers consider this a profound opportunity. Every interstellar object that passes through our solar system acts as a sample return mission without the spacecraft. We cannot yet fly to other stars, but fragments like TR3 Atlas come to us, carrying the chemical fingerprints of their birth environments. Each one offers a chance to test our theories about how planetary systems form across the galaxy. TR3 Atlas may not match the familiar comets cataloged in our solar system, but that difference is precisely what makes it valuable. Its CO2 excess, its reddish coloration, and its faint activity are all clues that somewhere out there, planetary systems build comets under rules we have yet to fully understand. The mystery now shifts from what TR3 Atlas is to how it became what it is. Was it formed gently in the outskirts of an alien system? Or was it blasted free in a violent collision, a fragment of a planetesimal ejected into interstellar space? Whatever the case, its presence here is a rare gift, a messenger from a system we cannot yet see. And if the past is any guide, TR3 Atlas's activity will only grow stronger as it approaches the sun. That makes continued monitoring essential, because what we see in the coming months may answer questions that no single observation can resolve. TR3 Atlas is not a static object. Like all comets, it evolves as it journeys through the solar system. Each day closer to the sun brings new changes, more sublimation, more dust, more outgassing. For scientists, that makes continuous monitoring essential. A single image or data set is valuable, but only by tracking the object over weeks and months can its true nature be revealed. The August 6th spectra from Webb showed chemical signatures. The August 23rd image from SONIR revealed the first trace of a tail. Future observations from both ground and space will be needed to show how that activity develops. Will the tail grow brighter and longer, confirming TR3 Atlas as an active comet? Will its chemical output remain dominated by carbon dioxide, or will new gases emerge as different layers of ice are exposed? Only by watching continuously can those questions be answered. This is where international cooperation becomes more than a formality. No single observatory can follow TR3 Atlas every night. Weather, geography, and telescope time are all limiting factors. But when astronomers coordinate across continents, they can build a near-continuous record of activity. In effect, the world's telescopes form a relay, handing the object from one night sky to the next. The urgency is sharpened by the object's trajectory. TR3 Atlas is interstellar. It will not return. Once it swings past the sun and recedes into deep space, it will be gone forever, beyond the reach of our instruments. That makes every observation window precious. Astronomers are racing against time to record as much as possible before the opportunity vanishes. Monitoring also carries scientific weight beyond this one object. By documenting TR3 Atlas's behavior in detail, astronomers can compare it to earlier visitors, Oumuamua and comet Borisov, and prepare for future interstellar arrivals. Each one adds to a growing data set, slowly transforming speculation into understanding. For TR3 Atlas, the stakes are high. Continued monitoring may confirm whether it is simply a carbon dioxide-rich comet or something stranger, a planetary fragment, a hybrid body, or a new category entirely. But regardless of the outcome, the process itself, watching an alien object evolve in real time, is one of the most extraordinary opportunities in modern astronomy. For most discoveries in astronomy, the public hears only the final story. A spacecraft completes its mission. An observatory publishes results, and polished images and explanations are shared months or years after the work is done. But with TR3 Atlas, something different is happening. The world is watching science unfold in real time. This means the public sees the process not as a neat conclusion, but as a series of evolving steps. At first, TR3 Atlas was only a faint moving dot. Then it became a candidate comet, then a suspected asteroid, then perhaps even a planetary fragment. Each new observation shifted the interpretation, and each shift was broadcast almost immediately. For many outside the field, this rapid change looked like confusion. For scientists, it was progress. Real-time science is rarely tidy. Data arrives raw and imperfect. One observatory catches a faint trace of activity, while another detects unexpected chemistry. The challenge is to assemble those fragments into a coherent picture before the opportunity slips away. With TR3 Atlas, the urgency is amplified. Once the comet passes the sun and fades back into interstellar darkness, there will be no second chance. For the public, witnessing this process is both exciting and unsettling. It is exciting because it gives direct access to discovery as it happens, without the long wait for final answers. It is unsettling because the conclusions are provisional, subject to change with the next observation. But this is the nature of science, a living, adaptive system that grows stronger through revision. TR3 Atlas is a reminder that discovery is not a moment, it is a journey. It is the long arc of questioning, testing, and correcting, carried out under the pressure of time. To follow its story is to watch knowledge itself being built, one faint image and one spectral line at a time. And as that story unfolds, one fact grows harder to ignore. TR3 Atlas is not simply a curiosity, but a comet in the making. Its tail is faint, its chemistry unusual, but its behavior aligns with what comets do. The next stage in its journey will test that conclusion further, as more observatories join in and more data streams in. The question now is not whether TR3 Atlas is active, but what will come next as it approaches the sun. The story of TR3 Atlas is still unfolding. Each new observation sharpens the picture, but the object has not yet revealed everything it has to offer. As it continues its journey toward perihelion, the closest point to the sun, astronomers expect its activity to increase. The faint tail seen in late August may brighten and extend. Dust and gases may surge, and Webb's instruments may detect new molecules as deeper layers of ice are exposed. But there are risks, too. Comets are fragile bodies. Some survive their passage near the sun, displaying spectacular tails that stretch millions of kilometers. Others disintegrate, torn apart by thermal stress and gravitational forces. TR3 Atlas's future is uncertain. Will it endure long enough for us to study it in detail? Or will it fragment, leaving only a cloud of dust to mark its passage? Whatever happens, the importance of monitoring cannot be overstated. Each stage offers unique information. If the comet brightens, astronomers will be able to measure its output with greater precision. If it fragments, the process itself will reveal clues about its internal structure and strength. Either outcome provides data that cannot be obtained once TR3 Atlas has left our skies. Looking further ahead, TR3 Atlas also sets the stage for how we will study future interstellar visitors. With every new object, astronomers refine strategies, knowing what instruments to deploy, when to expect activity, and how to interpret unusual chemistry. Oumuamua taught us about interstellar asteroids, Borisov about interstellar comets, and now TR3 Atlas about the diversity of compositions possible beyond the solar system. Together, they form the beginnings of a new field, comparative interstellar science. For now, the next steps are clear. Astronomers will continue pointing telescopes, large and small, at TR3 Atlas, gathering every bit of data possible before it recedes forever. The coming weeks and months will tell us whether it is a faint, carbon dioxide-rich comet, a planetary fragment, or something that does not fit any category we currently have. And when it finally vanishes into the darkness beyond the sun's reach, it will leave behind more than faint light trails and spectra. It will leave a record, one more piece of evidence that our galaxy is filled with worlds and fragments far different from our own. Each visitor is a reminder that the solar system is not alone, and that the space between stars is not empty, but alive with messengers from distant origins. The mystery of TR3 Atlas is not finished. It is only the latest chapter in a much larger story, one that asks, what else is out there, waiting to cross our skies?